Okay, so for a function y equals f of x, okay, the square root of this function is y equals the square root of f of x. Okay? So we're literally going to take an entire function and take the square root of that. Now, you could do this with any type of function, but in this course, we tend to stick to linear functions, quadratic functions. Okay? So we'll be focusing in on those today. However, you could do this for anything. You could take the square root of an exponential function if you want. You could take the square root of a trigonometric function or a rational function. Okay? But these are the ones that we're going to focus on today. So, for example, suppose we have this function f of x equals x minus 2, and we wanted to write the square root function in terms of x for y equals the square root of f of x. Well, what would that function be? How would you write it in terms of x? Yes?
Y equals the square root of x minus 2.
Yeah, exactly. Okay. Now, based on what you know about transformations, this is something that you should be able to do directly. Because essentially, what you're doing is looking at the square root of x, and then how is this one being transformed? What's the transformation that takes place to get y equals the square root of x minus 2? Are we stretching? Are we reflecting? Are we translating? Are we doing all of the above? We're translating, right? 2 units to the right. Okay? But what we're going to do today is work from the place of a table of values. Okay? So, because our starting point really, when we talk about the square root of a function, is the original function. Okay? So let's make a table of values for this original function, y equals x minus 2. Okay? So if x is negative 1, y will be negative 1 minus 2, which is negative 3. If x is 0, y will be negative 2. If x is 2, what will y be? 0. Yeah. Okay, if x is 2.5, y will be 0.5. Okay, if x is 4, 4 minus 2 is 2. If x is 6, this will be 4. And if x is 11, this will be 9. Okay, so let's maybe draw that first. Negative 1, negative 3. 0, negative 2. 2, 0. This is a linear function. 2.5, 0.5. So that's that guy right there. 4, 2, 6, 4, and 9, or sorry, 11, 9. There we go. Okay, so this is a linear function. I have to stand right in front of it when I draw the line, or else it goes wonky. That still went wonky. But there is our original function, f of x. Okay, now what we're going to do to get a table of values or some points that we can plot for the square root of the original function is work from the table of values, right? So, for example, when x is negative 1, this should be the square root of negative 3. So talk to me about that. Yeah. Yeah, we can't take the square root of a negative number, or we get a non-real or imaginary number, which is beyond the scope of this course. But the point is that we have to actually consider the domain of the original function when we take the square root of it, because square roots are only defined for radicands that are greater than or equal to 0. Okay? So there's no point here, right? No point here. Or these, you could say they're undefined. Okay. What about here? Square root of 0? 0. The square root of 0.5, now that's an irrational number. So let's just, I'm going to do it on my calculator. I'm getting about 0.71-ish. This is also going to be irrational. It's going to be the square root of 2. So that's 1 point something. 1.4. And I mean, I could have put 0.7 because really, when we're looking at decimal values like this, I'm going to be approximating the y value of that point anyway. And there won't be much difference than 0.7 and 0.71. Okay, what about this guy? 2, and this one? 3. Okay, I want to sort of add in one other point. So let's say that this is 3. What would 3 minus 2 be? What would the y value be? 1. Okay, and the square root of 1? 1. Okay, so we'll put that one in there too. And I'm going to do these guys in a different color. I'll do them in blue. Okay, so this guy's going to be in blue. Okay, so firstly, I can't put any points over here. I can put a point here. That works. When x is 2.5 rather, this is at about 0.7, so that's there. Okay. When x is 4 rather, y is 1.4, that's about there. So when x is 6, y is 2. When x is 11, y is 3. Okay, and I want to add this point in as well. When x is 3, y is 1. So this looks like this. And essentially, that is in fact a translation of the function y equals the square root of x. It's been moved 2 units to the left. Okay, any questions so far? All right, cool. So what happens to this graph when the x values are less than 2? It is non-existent. The graph is non-existent because the square roots of negative values are undefined. Okay, so another thing I want to talk about are the invariant points. So where did the invariant points happen? 2, 0. Yeah, invariant points are the points that don't change from the original to the square, in this case, the square root of the function. Yeah, so the point 2, 0, that is invariant. And what's another point that's invariant?
3.
Yeah, 3, 1, right? Okay, so let's talk about this because there's a specific reason why I added that point in there. Think about this. What values can you take the square root of that don't actually change the value? 0. Yeah, what else? 1, yes. Essentially what we're trying to answer there is when is square root of x equal to x? When does taking the square root of it equal the same thing? Now you can actually see this algebraically as well if you square both sides. And what you're going to get is x equals x squared. And if I equate one side to 0, this is factorable, right? It's equal to x times x minus 1. So there are 2 values of x for which this is true. When x equals 0 and when x equals 1. Okay, so if I'm taking the square root of a function, the function will always be equal to the square root of itself when the function is either equal to 0 or when the function is equal to 1, because those are the two values where taking the square root doesn't change the value of that number. Okay, so you may want to put a point in here. Invariant points occur when f of x equals 0 and when f of x equals 1. Square root of 0 is 0, square root of 1 is 1. Okay. Okay, so let's talk about domain and range. What's the domain of the original function? Yeah, x is an element of the real. So for y equals f of x, and the range for the original? What's the range of the original linear function? Same thing. Yeah. Y is an element of the real. Okay. What about the square root? What's the domain of that? Yeah, x has to be greater than or equal to 2. Okay, and that's because we specifically need the radicand to be positive. And in the linear function, the function is positive when x is greater than or equal to 2. Okay, what about the range? Right. Y is greater than or equal to 0. And this range is consistent for all radical functions, square root functions. Although, well, we'll see an example actually where the range is slightly different than this, but this condition must be true. You cannot take the square root of a function when the function is negative. So the caveat is that if the domain of the original function is always positive, let's say the domain is x is greater than or equal to 4, then the domain of the square root would be x is greater than or equal to the square root of that, which is 2, right? So sometimes you may see something a little bit different than this. However, this condition where the range must be positive or greater or 0 is true, because you can't take the square root of a negative value. Okay, so far so good? All right. Okay, so let's take a look at another one. So we are going to complete this table. Again, we're looking at a linear function, y equals 4 minus 2x. And then we're going to sketch the graph of this from the table of the linear function. Okay, so when x equals -6, y will be 4 minus 2 times -6, which is what? 16, right? Okay. When x is 0, 4 minus 2 times 0 is 4. No. Yes. Right? I'm getting a step ahead of myself. Okay, when x is 2, this is 4 minus 2 times 2, which is 0. And when x is 4, this is 4 minus 2 times 4, which is 4 minus 8, -4. Okay, so if we want to start with this table of values and plot this radical function, what we need to do is take the square root of all the y values. X values aren't going to change, but the y values will be the square root of the original. Okay, so for example, for this radical function, when x is -6, what is y going to be? 4. It's the square root of 16, which is 4. Okay. When x is 0, what will the value of the radical function be? 2. Yeah, because the original function is here, so the square root of 4 is 2. Okay. Now, the square root of, when x is 2, the original function is 0. So what will the square root function be? 0. Yeah. So if you want to kind of remember, this point is -6 root 16. That's where that 4 comes from. This point here is 0 square root of 4, because that original point is when y is equal to 4. This point here is 2 square root of 0. Okay? Now, one thing that I would always add to these sketches is plot the invariant points. So one of them happens here, but the other one will happen when y equals 1. So that point won't change. So I would put that in there. Okay? And now, what about when x is 4? Yeah, we can't graph, or we can't actually evaluate the square root of -4, so we wouldn't include that on the graph, okay? And in fact, this is an endpoint. Okay? Now, if you were to do this using transformations, then you would have to kind of rewrite this as the square root of -2 times x minus 2. And so essentially what we're doing is, if you look at, this is our b value, so we're horizontally stretching by 1/2 and reflecting, which is why it goes the other way. And then we also move 2 units right, which is why the endpoint is at 2, 0 and not at 0, 0. Okay, so there's not anything really new here. We're just sort of getting to that graph by a different means. We're using the linear function to get there instead of transformations. Yes?
Wait, why does it go through that line? Like, why did you add that extra point?
So why did I add that extra point? I added this point because I always sort of make a point of plotting the invariant points. And the invariant points will be whenever the original was equal to 1, which is here, or when the original is equal to 0, which is here. Because the square root of 1 is 1, the square root of 0 is 0. Yeah. Okay? So state the coordinates of any invariant points. Okay, so the invariant points happen firstly at 2, 0. Okay, now I believe that this is, what is this? Let's solve for it. Okay, the x value of the invariant point is going to be when 4 minus 2x equals 1. That's what we're looking for. Because we want to get an invariant point, we want to take this part, we want that to be equal to 1 so that when we take the square root of it, we still get 1. Okay, so this is how we could algebraically solve for this. If I maybe subtract 4 from both sides, I'm going to get -2x equals -5. Divide both sides by 2, x equals 2.5. And that looks about right. Okay? Sometimes when the x value is not like on a whole number, it's kind of hard to tell. Yeah?
Wouldn't it be x equals -3 over 2? Kind of, you did 1 minus 4.
Oh, shoot. This is -3. It's 1.5. Yes, you're right. 1 minus 4 is not -5. 1 minus 4 is -3. -3 over -2 is 1.5. Yes, that is correct. Okay, so that's our other invariant point. 1.5, 1. And essentially, the x value of 1.5 is the x value that makes the radicand equal to 1. And that's why I found it by setting this equal to 1, because that's what goes into the radicand. Okay? All right, domain and range of the radical function. So what is the domain of this function? X is less than or equal to 2, yeah. And the range is y is greater than or equal to 0. Okay. Now, how could you determine the domain algebraically? Essentially, we need the radicand to be greater than or equal to 0. So that's how you would figure it out. You would set this that piece, whatever goes in the radicand, has to be greater than or equal to 0. Okay? So if we solve this, let's say we add 2x to both sides. Actually, no, I'm going to subtract 4 because I want to like emphasize this point. You could do it that way too. I'm going to subtract 4 from both sides. You're going to get negative 2x is greater than or equal to negative 4. So if I solve for x, divide both sides by negative 2, what happens? Yes, exactly. This flips around. Okay? So we're going to get x is less than or equal to 2. Okay? Okay, so far so good? Okay, cool. Okay, so one thing that I want to sort of do is actually look at what happens to the function, the radical function, when the original function is certain values. So what I'm going to do here is I want to break up the value of the function. So firstly, one thing that we know is this is only defined when f of x is greater than or equal to 0. Okay, so that's one thing. The other thing that I want to talk about is the invariant points. Okay, so invariant points occur when the function is equal to 0 or 1. Okay, because again, take the square root of 0, you get 0. Take the square root of 1, you get 1. Okay, and we're going to kind of use these values of 0 and 1 to generalize what we will see on the graph by breaking the sort of range up using these values. So I'll show you what I mean. We're going to chart the value of f of x and the placement of y equals the square root of f of x. Okay? So I'm going to break things up using these two values that we get with the invariant points. F of x equals 0 and f of x equals 1. Okay, so firstly, if sort of that's our y-axis, right? There's sort of 3 regions that I want to keep track of. So let's say f of x is less than 0. Okay. F of x equals 0. So that's right here. Less than 0 is here. Equals 0 is here. The next one would be here, between 0 and 1. 0 is less than f of x, which is less than 1. F of x equals 1. And then finally, this last piece, f of x is greater than 1. Okay, and what I specifically want to look at is where is the graph of the radical compared to the original? Okay, so firstly, if the original is less than 0, what are we going to see for the radical function? Nothing. Yeah, undefined. Okay, what about if the original is equal to 0? What's going to happen with the radical? Yeah, it'll equal 0 as well. So this is an invariant point. Right? This one is also an invariant point when f of x equals 1. So we'll stick that in there too. Okay, so now let's look at this. When f of x is between 0 and 1, so that's right in here. Where is the radical function compared to the original one? in like simple terms. Okay, so between here and here, here's the original function. Here's the radical function. How would you compare the two? It's curved, okay. Is it less than the original? Is it greater than the original? Is it equal to the original? Yeah. So when the value of the original is between 0 and 1, the radical function will be greater than the original one. It'll be above the original one. Okay, so this is going to be above f of x. Okay, that's because when you take the square root of a number that's less than 1, that's between 0 and 1, you're going to end up with something greater than you started with, right? Let's say you take the square root of a quarter. What times itself equals a quarter? That would be a half, right? So when you take the square root of a number between 0 and 1, the square root is actually bigger than what you started with, okay? What about when f of x is greater than 1? So that would be like from here on. How could you compare? Yeah, it's underneath. It's under the original. Because when you're taking the square root of a number larger than 1, that square root will be smaller than the original, right? Square root of 16 is 4. Square root of 25 is 5. So this one will be below f of x. And actually, this can help you, give you a guide to get a rough sketch of the radical function without actually having to think about the table of values, right? If you just know, okay, these points have to stay the same, and then, okay, that's less than 1, so that's going to be above it, and then everything else will be below. You can use it as a guide. Okay? Any questions so far? All right. So what we are going to look at next is suppose we're going to look at various graphs and connect a radical function to the original or vice versa. Okay? So given the graph of y equals g of x, so that function over here is actually not defined in terms of x. We just have a linear function. We're going to graph y equals g of x on the same grid. And then we're going to write an equation for y equals square root of g of x in terms of x. Okay, so firstly, what points can we put in right away? Okay, we could, yeah. Where would that point go? 0, 3. Okay, yes. So you're getting like ahead of where I was going to go, but that's okay. We can certainly put that in because 3 is the square root of 9. Okay. Where I always start though is with the invariant points, right? So wherever the function's equal to 0, that's here. That will never change. And whenever the function's equal to 1, that'll never change, right? Now here the function is between 0 and 1, so it's going to go above and then below. That's sort of the general shape of the curve, okay? But you're right, I would actually get more specific than that. So what I would look for when I'm graphing other points are the y values that are perfect squares, because it's really nice to take the square root of a perfect square. So I'm going to look at here, 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 and here, and put the mapping of those points, right? So we got these two in it already. When y equals 4, that's right here, that's going to move down to 2. Okay, and then we've got this point, this point, this point. We already did when y equals 9, and that moved to here. So these are a couple of points that'll help us to get a rough sketch of that radical function. Okay, so again, what I did, I think I used the color blue too much, so I'll do it in red, is I looked to the y values that are perfect squares. Right? So square root of 9 is 3. That's where that point came from. Square root of 4 is 2. That's where that point came from. Square root of 1 is 1. Square root of 0 is 0. Yeah?
Wouldn't the graph just end right at x equals 0? Because,
Okay. Tell me why, though.
well, because you can't get
If x is less than 0, will the radicand be positive?
oh, right.
Yeah, because
Yeah.
we're taking the square roots of the y values, right? Now, if we wanted to come up with an equation for this radical function in terms of x, what would we have to do first? If we want to know this equation, y equals the square root of g of x, in terms of x, though, what would we have to do?
You have to make g of x.
Yeah, we got to figure out what the function g of x is, right? So this is a linear function. You can look at the y-intercept and the slope. Okay, so when I'm looking at slope, rise over run, pick 2 points that are on like the intersection of the grid marks. Like I'll go there and there. So it looks like I'm going down 3, right 4. Right? Or you could use the slope formula, pick any 2 points, m equals y2 minus y1 over x2 minus x1. Right? There's multiple ways of getting a slope. So it looks like g of x is y equals mx plus b. So negative 3 over 4x and then plus 9. Okay? So our radical function will be the square root of negative 3 over 4x plus 9. Yes?
I think I missed something. Can you like show how you did that again?
To get the original?
Like, yeah.
Okay, so the original function is a linear function, right? So I was going from y equals mx plus b, right? So the b is the y-intercept. That happens at 9. And then to get the slope, I used rise over run. So I just picked 2 points that happen sort of on the intersection of the grid marks. And I went down 3, right 4. Yeah? Okay. Okay. So now we have another function, y equals square root of f of x. So we're given the radical function here. And now we actually want to create the original. That's kind of the direction that we're going in. Okay? So first, let's talk about the invariant points. What are the invariant points? What will the invariant points be once we graph the original? Yeah, negative 4, 0. Yes. And negative 2, 1. And in fact, just by looking at the invariant points, you should have enough information to get the original function. Because when you're looking at a linear function, all you need is 2 points. Connect them, there's your line. Okay, so if I take this point and I connect them, there's my linear function. Okay, now check to make sure that that works out though, right? So for example, this point 4, 2, that 2 came from square rooting the original. So 2 was the square root of what? It's the square root of 4. That kind of makes sense. Okay. So there's the original. But I just got it by connecting the 2 invariant points. In fact, that's a really bad diagram because, sorry, I have to redo that. I need to learn that I can't graph sideways. I always try and do it, and it doesn't work. Okay, so that's better. Okay. So as soon as you have 2 points on a linear function, you got the entire function. Connect the dots, you make a line. So you can go straight from the invariant points and get right there. Okay. Now, if we wanted to write an equation for the original, again, we can use slope and y-intercept. So here the y-intercept is at 2. And it looks like to get from this point to this point, and I'm just using the invariant points because those are sort of the most obvious to me, I'm going up 1 and right 2. So that slope, rise over run, would be 1/2. 1/2 x and then plus 2. Right, this is our b value. And the slope, 1/2, is the m value. Okay, so far so good? Yeah.
I got 2 as a slope. All right, never mind.
Okay. Keep asking those questions though, because in my experience, if I were to estimate, I would say half of the time when there's a discrepancy between me and you guys, I'm the one who's wrong. And that's already happened today. Okay. So we talked about linear functions. Now we are going to talk about quadratic functions. Okay. Now, what I want you to think about is before we even start, radical functions are only defined when the function itself is positive. With linear functions, that's really easy. There's like one point where it crosses 0, and either to the right or the left of it, the function's positive. Okay? There's a lot more possibilities with quadratic functions because they can open up, they can go open down, they can, right? So if you think about where the function is positive, you could have this, you could have this, you could have this, you could have this. Those are all different places where the quadratic function can be graphed on the coordinate plane, right? We're going to get a bunch of situations here because in this situation, the radical function will be defined here. In this situation, the radical function will be defined here because these are the ones, these are the sort of regions where the original is above the x-axis, where f of x is greater than 0. Okay? Here, where will the radical function be defined? Yeah. Everywhere. Yeah, because in this particular instance, the original function is always positive. So the radical function in terms of the domain will happen everywhere here. What about here?
Nothing.
Undefined. Yeah, the original function is always negative. So this is undefined. Okay. The only other thing that you might see, this is interesting, I like this one, so I'll put it up, is you could have this. Where would that be defined? Yeah, there's only one point where the radical function will be defined. Okay, now the red part that I drew in, that is not what the radical function will look like. That would just be the domain of the radical function. Okay, that's important. All right, so let's take an example. Identify and compare the domain and range of y equals x squared minus 4 and y equals the square root of x squared minus 4. Okay, so firstly, we got to think about our knowledge of transformations to graph this thing. Okay, what would the base function be for y equals x squared minus 4? Y equals x squared, and then what's happened to it? It's moved down 4. Yeah, so that's where the vertex is going to go. It will go at -4, 0, because the original one would have been here, right? Maybe let's graph the original one first, then we can move everything down 1. Down 4, not down 1. Okay, so the original would have had like -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. Those points all need to be moved down 4 units. So -2, 4 is going to move to -2, 0. -1, 1 is going to move to -1, -3. 0, 0 will move to 0, -4, right? And then we know that there's some symmetry here, so there are the other points. Okay? You could even plot -3, 9 will go down to down 4. So there we go. -3, 5, and then that'll be this point here too. Okay? So here we go. There's the original. Okay? What is the minimum value of the original? Yeah, the minimum value. Yeah. Okay, so that would be more like the range. What's the minimum value of a function? Do you know where to look for that? Yeah, it's the smallest y value. Okay, so the minimum value is -4. The vertex is the coordinate of that point. So that would be 0, -4. Okay, what direction does this open? Up. The domain? Yeah. The range. Yes. Okay, or just to throw in some interval notation, you could also do that. -4 infinity. Okay, so let's look at the radical function now. Okay, maybe let's actually start by graphing the radical function. All right, so here's a nice little trick that I like to do. First, what points do you think I'm going to plot first to get the radical function? Okay. The zeros and the ones, the invariant points. Yes. Okay, I'm going to plot the invariant points because I know that those don't change. So those are going to stay in the same place. These are going to stay in the same place. Okay, now I try and plot one other on either side. So I'm going to pick whenever y is equal to 4, what's the square root of 4? 2. So that point's going to be there. And I kind of botched this a little bit, but it should be like here. Okay? Where's this thing undefined? Yeah, between -2 and 2, there aren't going to be any values for the square root of that function. So here we go. There's the radical function. So I didn't choose 5. I eyeballed where the function was equal to 4. So I was looking here. And I'm like, okay, that's going to move down there. And that's going to move down there. Because the square root of 4 is 2. Yeah.
And you can also do the 9s as well for more reference.
So the problem with the 9s, you could, but I didn't really get that far. Right? Like you could put this at 3, but we don't see that because it's been shifted down. You know what I mean? Like where the original 9 would have been has been moved down to 5 because of the transformation. Yeah. Yeah. Okay. Good so far? Yes. So I look here, here, and then the next perfect square, which is 4. The zeros and ones aren't going to move. The 4s will move down to 2. Yeah. Okay. once we have that graphed, what's the domain of this function? Yeah, so there's two regions where this function is defined. X less than or equal to -2, or x greater than or equal to 2. Okay, now I know I'm sort of being picky here. Could you have the word and in between those two inequalities? No, because you can't have a number that's both less than -2 and greater than 2. Okay, now, do you know what this would look like using interval notation? Solid no. Okay, so let's talk about that. This piece is the lowest value is -infinity, the highest value is 2, and it's inclusive. This guy, the lowest value is 2, -2. 2, and the highest value is infinity. Okay, and then we use a symbol in between, which comes from set theory, and it's the union symbol. It means we're joining these two regions together to create the domain. The union symbol is an elongated U. Kind of looks like that. So we're saying this interval unioned with this interval makes the domain. Okay. All right, what about the range of this function? Yeah.
I don't know how to describe it in words, but know how to draw it.
Oh, yeah, you could do it as a graph. So you could do it this way too, I suppose. Is this what you mean?
Kind of, where it's. I'll draw it out for you.
Okay, I'll take a look in a sec. Okay, but in the meantime, let's talk about the range. What is the range of the radical function?
So where it's one.
Okay, all right, we'll talk about that. No, but
That's why I asked you this.
yeah. Okay, what's the range of the red function? Yeah, greater than or equal to 0. Okay, so the question, by the way, was could you do this? Which one was on the?
It was because 2 has to be.
Yeah.
Yeah, it has to be.
Okay, so I'll talk. So the question was about the double inequality, right? Like -2 less than or equal to x less than or equal to 2, that kind of thing. So that is actually what you would do if the domain is sandwiched between two finite values. So if it was this part, if this whole thing was upside down, that would be the domain.
Oh.
Yeah.
Okay.
Yeah.
Sick.
Okay. Okay, so I sort of did this a little bit, but using key values can really, really help to firstly determine the domain and range and actually graph the one from the other. Okay, so X-intercepts. X-intercepts occur when y equals 0. Will the X-intercepts change? No, those are actually invariant. Okay, so these happened at -2, 0 and 2, 0. These guys are the same because wherever y is equal to 0, we have an invariant point. Okay, so X-intercepts will not move anywhere when we take the square root of a function. Right, so these are invariant. Y-intercept. What was the y-intercept of the original? -4. Okay. What's the y-intercept of this one? There is none, yeah, because it's not defined when x equals 0. In general, this will be undefined if the original y-intercept is less than 0, right? Okay, maximum value of the original. Infinity, yeah, there is a maximum value. It's just not a finite value. Okay, what's the maximum value of the radical? What's the square root of infinity? Also infinity. Yes. I find this fascinating. Infinity actually has different sizes. I think that's so interesting. What's that? Well, no, but yeah, if you think about it, like think about integers versus natural numbers. Integers are positive and negative whole numbers. Those are infinite, right? Natural numbers start at 1. So the natural numbers are actually half the size of the integers, but they're both finite, or infinite sets rather, right? Wild. Okay. What's the minimum value of this guy? -4. What about the minimum value of this one? 0, yeah. Okay. All right, let's look at this one. We are going to graph the radical function on the same grid as the original. Okay, so firstly, where's the original undefined? Like, what do we not have to worry about? You guys okay over there? Yeah? Where do we not have to worry about graphing the radical function? Yeah, so we're not going to worry about any of this or any of that. Maybe I should have done that in another color. I'll graph the radical in red. Okay. So what would the next points be that you would graph?
1 and 0.
Yeah, so wherever the function is equal to 0 and whenever the function is equal to 1. Okay? And then in this case, I would probably graph a few other points just to guide myself. So I'm going to look at where the original is 4 because that's going to drop down to 2. Square root of 4 is 2. So right here, oh, that's bad. Hold on. I can do better than that. And here. And then there's one other point that you want to have pretty accurate.
You just want to take the square root of 8.
Yeah, take the square root of the max point of 8 and plot that one. What is it?
2.
Yeah, so I would approximate that one too. Right, and there we go. Yes. Yeah, this is where if you were writing out the domain for this one, you could use the double inequality here. Yeah. All right. So far, so good?
Yes.
Okay. All right. So determine the domain and range of this and use technology to help. We're going to do this without technology, but you could do it with technology if you wanted to. But we know enough about transformations to be able to graph this by hand. Okay? It's a good review. All right, so let's take a look at the original function. What would the base function for the original function be? Y equals 2x squared plus 3. Y equals x squared, yeah. So if we look at y equals x squared versus y equals 2x squared plus 3, what transformations have we applied? Vertical stretch of 2. What else? Yep. Yeah. Okay, so when you are graphing from transformations, I always start with this, apply the stretch first. Okay, so what I mean by start with this and apply the stretch first, for a quadratic y equals x squared, I'm hoping that you guys have these points sort of in your head, right? At least those 4. Yeah? -2, 4, -1, 1, etc. Okay? So what I'm going to do is I'm going to stretch those by a factor of 2 vertically. Where is this point going to go? -2, 4. If I just think about the vertical stretch factor, -2, 8. Exactly. All the y values will get doubled. So I'm going to do this in like a different, I'll do little x's. So -1, 1 will go to -1, 2. This won't move at all. Okay? 1, 1 will move to 1, 2. And 2, 4 will move to 2, 8. Okay, so that's just the stretch. Now what do I need to do? Move everything 3 up. Yeah, so I'm going to do this, let's say, in green. Okay, so 1, 2, 3. 1, 2, 3. Taking these X marks. 1, 2, 3. Here's the next one, up 3. 1, 2, 3. And this guy, 1, 2, 3. And those are the things that I want to graph. There is my parabola. Okay, and then what I would probably do is I would erase all of the red x's because I don't want to confuse myself. But definitely I would put those in as a guide because you have to apply stretches first. Then you can do the translations. Okay, so I'm going to erase these now because I've already gone up 3 from all those points. Okay? Okay, so let's talk about the domain and range of the original. What's the domain of the original? Yeah. Okay, so for y equals 2x squared plus 3, the domain is x is an element of the real numbers. X can be anything. Put anything into that function. What about the range? Ooh. Yeah. Okay. So now let's consider the radical function. Okay, so usually I start out by plotting invariant points. What can you tell me about that? There are none. Yeah, because y will never equal 0 and y will never equal 1 in the original function. So no points are going to be mapped to themselves. But there are things that we can do to try and see roughly what it will look like. So firstly, where would this vertex go? This point 0, 3, where is that going to move to? Yeah, 0 square root of 3, right? So square root of 3, is that about 1.7? Yeah. So 1.7 will be here. Right? So this is the point 0, root 3. Root 3 is about 1.7. Okay? Then I would do a couple of points where you see perfect squares, because then again you're going to get whole numbers, right? So wherever the original is equal to 4, the radical function will be equal to 2. So that's about here and here. Okay, and then the next perfect square is 9. So that's here, almost at when x equals 2. So this is going to move down to 3. And this one will also move down to 3. Okay, and so we get this sort of picture like this. It actually looks like another parabola, but it's wider. This one is y equals square root of 2x squared plus 3. And so there is a ton of variation that you can see when you're taking the square root of a radical function, depending on, or sorry, the square root of a quadratic function, rather, depending on where the original parabola was on the coordinate plane. Okay? So let's talk actually then about the domain and range of this guy. What's the domain of the radical function? Yeah, x can be anything. What about the range? Okay, so that's interesting. I'm not sure if you guys just heard what was said. I know some of you are listening and some of you aren't. So if I put the range is greater than or equal to 1.7, that's actually not correct. Yeah, root 3, yeah. It's really close. Root 3, because root 3, where's my calculator? Root 3 is 1.73, right? So actually, if you put in a value of 1.7, it would be too low. Or if the 1.7 was rounded up, it might be too high. So exact values. Okay. So that's it actually for today. But I do sort of want to talk about what you might see when you graph various parabolas and their radicals. Okay, I want to try and generalize this because we can make some generalizations based on the position of the original radical. Okay, so let's do that. In general, okay, if we have these types of parabolas, and I'm not going to define them in terms of a quadratic. I'm going to define them in terms of where they are in the coordinate plane. So we could see this. We could see this. Okay. We could see this. Or we could see this. I'm going to have to squish it, but it's okay because we're not going to have to write much for the radical one, right? Okay, so if you see this guy, make a little chart here. Where will the radical function be defined? Yeah, it's going to be to the left of this x-intercept and to the right of this one, right? So this will look roughly like this. There's the other one. Okay, if we see this second situation where and essentially in the first and the second, there are regions where the original is positive or negative. Okay, where will the radical function be defined here? Yep.
Inside the parabola above 0.
Yeah, like in between the two x-intercepts. So like here and here. And actually, I didn't put in a value here, but this is usually lower. Unless it's 1, unless that max value is 1, it'll be underneath it, because let's say that's a 4, the max will now be at 2. So it's usually a little bit sort of like that. It's not quite parabolic, okay? In this kind of scenario, where the original function is above the x-axis, the radical function will be defined everywhere. But it'll look actually like another quadratic, but it'll be like sort of lower and wider, right? So this guy's going to look more like this. And again, I didn't put actual values in here, but I would make a note, lower and wider. Oh my goodness, what happened there? Okay, and then here, undefined, yeah. Okay. Okay, any questions with that? All right, so that's it for today.